we've mentioned that reaction rates depend on temperature. Temperature is something that can vary a lot, so it would be pretty inconvenient if we had to redo our rate calculations for every single temperature that we encounter in a laboratory. Fortunately, we have an equation due to Svante Arrhenius in 1889, based on some work of Van Hoff, which relates the rate constant to whatever the present temperature is. So we have the rate constant is equal to some factor times some exponential here. The rate constant we can think of as the number of successful reactions which happen every second. Well, the constant term represents the total number of collisions between molecules which happen every second, and then this exponential term represents how many of them are successful. So number of collisions times probability of success gives you the total number of reactions per second. Now, within this exponential term, we see that there is this EA, this is the activation energy, the amount of energy we have to supply in order to get from one side of the reaction to the other. Now, note that this is a negative exponential. So as the activation energy gets larger, and this term becomes larger, this negative means that this whole term here is going to get smaller. So our rate is going to go down as we get a larger activation energy. Likewise, here we divide by temperature, which means that this term is going to get smaller as temperature gets larger. But because of this negative exponential here, that means that the whole exponential term will get larger as the temperature goes up. So that's our relationship. If we increase the temperature or we decrease the activation energy, that's going to increase the rate of our reaction. Now, a handy relationship is that our reaction rate is going to double every 10 degrees Celsius for many common reactions. This is very approximate, but this tells you why you can have such a huge difference in reaction if you have it at a high temperature versus a low temperature. Between 0 degrees Celsius and 100 degrees Celsius, you may have increased the reaction rate by 2 to the power of 10. Now we can write this equation in a linear form, and what we do is we take the natural log in order to get rid of this exponent here. Now when we do that, we can write that the natural log of our rate constant is equal to minus the activation energy over the gas constant times 1 over the temperature. This is going to be our variable, plus the natural log of our frequency factor. So this has our form of a line, y equals mx plus b. It's 1 over t, it's x. This minus e over r is our slope. So if we plot this, then whatever we get for our slope, we can set it equal to this term. And of course, we can set our frequency factor equal to wherever we intercept on the plot. We can use this equation twice, write it down for one rate constant and one temperature, and then write it down again for a second rate constant and a second temperature, and then divide those two equations. And if we do that, we'll get this equation, which is the 2-point form. So the natural log of the second rate constant divided by the first rate constant is equal to minus the activation energy divided by the gas constant times 1 over the second temperature minus 1 over the first temperature. Now this is very useful for comparing rates at two different temperatures. So if we already know one reaction rate and one temperature, and we've solved for the activation energy, then we'll be able to calculate the rate of our reaction at any other temperature. A caution about the 2-point form. Students find it very tempting when they are given a list of data for rate and temperature, and they're supposed to find the activation energy, to use the 2-point equation, because they recognize that there's the rate constants and there's the two temperatures, and that plugging in would be an easy way to get EA. Now the problem with that is that what you are doing is you're essentially selecting arbitrarily 2 points of this data set and figuring out EA from those points. Now the proper way to figure out what the activation energy should be is to go ahead and plot all the points and do the linear regression to get this line, which averages them all out. And then the slope here is going to be equal to negative the activation energy divided by the gas constant. Now you can see you get very different results if you compare it to just considering 2 points and compared to actually considering all of the points. Now, of course, if there's no noise in your data, if it's all collinear, then it's not going to make any difference. But because we don't know that, we're going to want to go ahead and whenever we have a set of data, we're always going to use this method in order to figure out what our activation energy is, rather than this method. Let's say that we have this reaction where we have the decomposition of dinitrogen pentoxide, and it decomposes into nitrogen dioxide and oxygen gas. And we perform a couple of experiments. We perform an experiment at 20 degrees Celsius, and we measure this rate constant. And we perform an experiment at 40 degrees Celsius and measure this rate constant. Actually, those might be several experiments to get these rate constants in the rate equation. What then is the activation energy? Well, it's probably best to use the 2-point Arrhenius equation. For one thing, because we don't care at all about the frequency factor. And this form doesn't involve the frequency factor. It's already gotten rid of for us. So we can go ahead and plug in our 2 rate constants and our 2 temperatures. And then we just have to solve for our activation energy here. Now, a caution, if you haven't done this kind of math for a while, some people think that they can fix this and just flip these numbers up top when they wind up dividing this quantity on both sides. That's not the case. You'll have to do the subtraction first and then divide. So we'll have to do this over here. And when we do that, though, we will get kelvins up in the numerator eventually. So that will cancel out this kelvins. And we'll be left with units of joules per mole. When I multiply those all out, I get an activation energy of 8,056 joules per mole. As a follow-up question, now that we know the activation energy, let's see if we can figure out what the value of our rate constant for this reaction will be at 50 degrees Celsius. So we already know, because we know that in general, our rate is going to go up with temperature, that we should probably get a larger value. It might not be true for endothermic reactions. Well, we can use our Arrhenius equation again. We'll stick with the 2-point form here, since really we're just looking for this missing rate constant. And so we can go ahead and plug in what we already know for one of our rates. And we'll want to use the temperature, which goes along with that rate for T1. And then now we're trying to figure this out at 50 degrees Celsius. So that's going to be our T2. 50 degrees Celsius is 323 kelvins. Now we can plug in what we found for our activation energy, 8,056 joules per mole. So now all we have to do is just crunch all these and add this on both sides. By the way, I've used one of our log rules. If we have the log of something divided by something, that's the same of taking the log of the first thing minus the log of the second thing. So that's how I separated those out down there. When I do this, I get the natural log here is equal to minus 6.28. So now I'm going to need to exponentiate both sides to get rid of that natural log. And when I do that, I get a rate constant of 0.0019 inverse seconds. And the inverse seconds I know have to be my units, because the unit's here. Now note that this is fairly similar to our other rate constants, but it's a little bit larger. So it definitely seems like a sensible answer. So we can definitely change the rate constant by altering the temperature. We also have this variable to work with, the activation energy. We can change the rate constant if we can find a way to change that activation energy. The way we would do that is through what's called a catalyst. A catalyst is a substance which speeds up our reaction without being consumed by the reaction. Now that means it's not consumed overall. So it might break apart during the process, but it would be regenerated by the end of the reaction. And what this does is it provides a new path with a lower activation energy than the path we had before. So a smaller EA means that this value is going to increase. Now, how does this catalyst work? Well, there are a few ways. One is that we can form better intermediates that give us this lower energy path that we can take. We can break our reactants into more reactive forms that require less activation energy. Might also change them in some way. For example, it might polarize the bonds of the reactants to make them more reactive. So an example of a catalytic reaction, we have hydrogen and oxygen combined to make water. We can, of course, start this reaction with a spark and get an explosion. But even if we just have hydrogen gas and oxygen gas together, we can make this reaction happen by providing a catalyst. And so a catalyst might be where we have this platinum here. And so the platinum, when the oxygen and the hydrogen reach the surface, they adhere to the platinum and they sort of break apart. Their bonds weaken. They're essentially atomic hydrogen and oxygen now. And since these bonds have already been broken, then it's much easier for the hydrogen and the oxygen to combine together to produce the water. Now, we might also have something called an inhibitor. So an inhibitor is where we have something else binding to our sites in our catalyst. And so if our inhibitor is on these sites, then our other reactants can't access them. And so it's going to inhibit our catalysis from occurring. These are also called a poison because they poison the catalyst and make it ineffective. We're going to break catalysts into three broad categories. One is homogeneous catalyst. This is where the catalyst is in the same phase as the reactants, i.e. everything is gaseous or everything is solid or everything is liquid. We might instead have a heterogeneous catalyst where we have the catalyst in the solid phase and reactants in the liquid or the gaseous phase. We can also have enzymes. These are large biological molecules which act as catalysts. And they might be either homogeneous or heterogeneous. They're kind of in between. Now, if you're an organism, you have an energy budget. You're trying to be much more efficient than any of the other organisms in your ecosystem. So it's a big advantage to be able to use an enzyme in order to perform a reaction. So a lot of biological reactions are mediated by enzymes. Actually, the same thing in industry. You want to use as little energy as possible to produce your product. So in general, about 90% of all industrial reactions involve a catalyst of some kind. An example of a homogeneous catalyst, chlorofluorocarbons were once used as refrigerants to run your freezer and your air conditioner and your automobile. And the problem was that they would catalyze the reaction of ozone breaking down into regular oxygen. Now, ozone absorbs ultraviolet light, so it provides some shielding for the Earth. And as a problem, these chlorofluorocarbons escape into the upper atmosphere, and they catalyze this reaction. And because they're a catalyst, they are not consumed by the reaction, so they're free to go on and perform this reaction again for other ozone molecules. And they're very persistent and consume a lot of ozone. Now, we have since banned chlorofluorocarbons to be used as refrigerants. And so now the ozone has had a chance to recover. And since everything's in a gas phase here, this would be a homogeneous catalyst. Example of a heterogeneous catalyst would be your catalytic converter. These use things like platinum and palladium and rhodium and copper and some other things in order to convert exhaust gas, such as carbon monoxide and nitrous oxide, into carbon dioxide and nitrogen gas, which are much less harmful. Amylase is an enzyme which aids in the digestion of starches, converts them into sugar. So when you eat something that's starchy, like maybe potato chip or something, you might notice a slight sweet taste in your mouth as you're chewing. And that's because the amylase in your saliva is breaking down the starch in the potato and converting it into sugar.